Welcome back. In a previous segment, we discussed the best case and worst case time complexity analysis. In this segment, we introduce a third kind of such analysis, namely average case time complexity. Now remember the previous observation that even given a fixed size n of the input to the algorithm, there may be different possible runtimes among all of the possible problem instances of that size. Now, instead of considering the best case and the worst case, in this segment we're going to consider the so-called average case time complexity analysis. Now, this is defined again as a function f of n, where n is the size of the input, and f of n returns the average number of primitive operations that are needed by the algorithm over all possible problem instances of size n. So here, instead of considering the best case or the worst case, we're going to consider all possible cases of all problem instances of a given size n, and then we're going to compute for each one of them the number of primitive operations needed by the algorithm, and then we're going to finally compute the average of all these numbers. So clearly this approach is going to require quite a bit more work than the previous two approaches, but let's illustrate it on a simple example. And again, I'm going to use the linear search algorithm. As always, the first step in time complexity analysis is to pick the type of primitive operations we're going to count. And of course, we're going to stick with the comparisons. Then, we're going to count the number of primitive operations that the algorithm executes in the best case, the worst case, and every other case in between. We're going to add all these numbers and divide by the number of cases to get the average case time complexity. So as we already discussed before, in the best case, the algorithm executes 3 comparisons. Now, in the next case, that is when the target object is equal to a sub 1, how many comparisons do we have? Well, there are 2 comparisons in the first evaluation of the while loop condition. Since this condition is true, we execute the first iteration, we go back to the loop, and then this comparison is evaluated to true, and this comparison now is evaluated to false because target is equal to a sub 1. So we've done a total of 4 comparisons. We exit the loop, and then we have one more comparison here to determine the return value. In this case, I is equal to 1. So in this case, we have a total number of comparisons equal to 5. So we keep going through all the cases for each possible position of the target in the sequence until we get to the case where the target is equal to a sub n minus 1. Now in this case, we need to go through all the elements in the sequence, and this happens after n iterations. So we're going to need 2 times n comparisons in that case, plus 1 comparison here for a total of 2n plus 1. Now remember, there's one more case, which actually is the worst case, which is when the target object is not in the sequence. Now in this particular case, we need to do all the work we did for the previous case, plus 1 extra comparison here in the n plus 1 iteration to realize that we are past the end of the sequence. So we're going to get a total of 2n plus 1 comparisons plus 1, or 2n plus 2. So notice we have now the sum of all the numbers of primitive operations executed in every case. So before we divide by the number of cases, which is n plus 1, let's try and simplify this sum. The first thing to do is to rewrite every one of these expressions except the last one as 2 times an integer plus 1. So 3 is equal to 2 times 1 plus 1. 5 is equal to 2 times 2 plus 1, etc., etc., until the last one, which is already written as 2 times n plus 1. And let's leave the last term unchanged. Now the advantage of writing these numbers, these odd numbers here, like we did, is that now we can see a pattern. So we're going to focus first on the terms 2 times 1, 2 times 2, 2 times n minus 1. We're going to group them together and factor the 2 out. So what we get is 2 times 1 plus 2 plus dot 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 plus n. Now remember, we still have to account for this one, and this one, and that one. And how many of those are there? The answer is n of them. So we have n, 1 plus 1 plus 1 dot 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 plus 1 n times. So this number here is equal to n. And of course the last term does not change. Now for the next step, we're going to keep this expression unchanged, and then we're going to group this n plus 2n plus 2 to get 3n plus 2. Now remember, the runtime of the algorithm in the average case is this sum divided by the number of terms in the sum, which is n plus 1. So f of n then is equal to this number that we just computed divided by n plus 1. This computation is basically the average of all these numbers. Now all we have to do is to compute the big theta relationship for this function f of n. Well, we already proved in a previous lecture that this sum of the first n integers is big theta of n squared. Now we're going to use that fact. So this term grows like 2 times n squared, and therefore f of n is big theta of a fraction where the numerator is the polynomial of degree 2 shown here, and the denominator is the polynomial of degree 1 shown here. All we need to do is to simplify this fraction. Now in terms of big theta notation, the numerator here, of course, is big theta of n squared because it's a polynomial of degree 2. So we can simplify that on the top. And the denominator here is a linear or polynomial function of degree 1, so it's big theta of n. So in terms of big theta, we could simplify the denominator to n. Of course, the plus 1 does not matter when n gets large enough. So in conclusion, f of n is big theta of this expression, which of course we can simplify to big theta of n. So the bottom line here is that the average time, or the average case time complexity of the linear search algorithm is on the order of n. It's a linear time complexity in the average case. Now let's double check that this result makes sense, or at least it's a possible result. Well, remember, the best case was constant time when the target is here. The worst case was linear time when the target is not in the sequence. So clearly the average case must be somewhere between the best case and the worst case. And at least linear time is definitely in the right range. Now the other thing to observe is that actually the average time is closer to the worst case time. In fact, it's the same order, linear. So that is the complete average case time complexity analysis of the linear search algorithm. Now, stepping away from this particular example of an algorithm, let's think about the average case time complexity. How useful is it? And also, what is the main drawback of this kind of time complexity analysis? Well, the main drawback, besides the fact that it's much more complicated and much more mathematically involved than the other two types of time complexities we've talked about so far, the main drawback is that the only way you can perform such an analysis is by making assumptions that I haven't made explicit yet. So let me tell you what I mean. The assumption comes in as the process you use to compute the average case. So for example, here to compute the average case, what I did is I summed all the values corresponding to each case, and then I divided by the number of cases. But this analysis makes a strong assumption, namely that every case out of all the possible problem instances are equally likely. The reason I made this assumption implicitly is because I added all of the numbers together and then divided by the total number of cases. The only way this works is when, if I took a random problem instance, they would all equally likely to end up being chosen. But that's not necessarily the case. Depending on the problem you're solving, some cases may be more likely than others. For example, if you have a sequence of 5 integers and you pick the target randomly in a set of 1,000,000 integers, it's much more likely that the integer you're looking for, the target, is not in the sequence. In other words, what we call the worst case scenario may be much, much more likely than the other ones. So in that case, this formula does not apply. The average would have to be weighted, or every term in that sum here would have to be weighted by the probability of each case occurring. So in our analysis here, we made the assumption that all the probabilities were equal. That's why we just had to divide by the number of cases. But in reality, the possible inputs to the algorithm could be distributed in many different ways, where some cases are more likely than others. So the only way to perform such an analysis is either to know the distribution of the problem instances, or to make an arbitrary assumption if you don't know any better, like we did here. But of course, there's no guarantee that the assumption we made matches the reality. So it could be, for example, that the best case, or cases that are closest to the base case, are much more likely than the worst case. And in that situation, it could be possible that the runtime of the algorithm on average would be less than linear. Maybe it would be log n, or maybe it would be closer to a constant time. So the main drawback of this average case time complexity is that either you don't know the distribution of inputs and then you have to make hypotheses or assumptions, or you do know the distribution, but either way, there are a lot more computations to perform to get the result. And remember, even if you get an accurate average case time complexity, the average case does not tell you anything about the worst case. So, say if the average case was linear but the worst case was n squared, knowing the average case time complexity does not guarantee that in some cases you will get a much worse runtime. For example, n squared. It's not the case here, but it could happen. In other words, the average case time complexity is not always the same as the worst case. So, keep that in mind, and from now on, you are assumed to be familiar with the best case time complexity, the worst case time complexity, the average case time complexity, and the advantages and disadvantages of each type of analysis.